deal with, the PBX manufacturer. And in theory, they need to have one point of contact for trouble and engineering and all of those fun things. Companies that aren't in the PBX business would have a different approach. They would say, well, you don't really want to use the PBX to do this. What you want to do is go buy some general purpose computers and run our software application on it to do all of the functions of a PBX plus all of the other things, and you can just forget about this PBX business altogether. This idea is called a soft switch, and replacing your PBX with a soft switch. As soon as we start talking about replacing your PBX with a soft switch, we have to back off and say, well, what exactly is a PBX? A PBX is a telephone switch, and a telephone switch is a computer. And just as in your desktop PC you can plug cards in that terminate phone lines, on a PBX, this computer, you can plug cards in that terminate phone lines, but instead of being able to plug in 3 or 4 cards, you might be able to plug in thousands of cards. And then a computer program takes information coming in on one of these cards, called a line card, and transfers it to another one in order to effect the communications from one telephone to another. Now, when we talk about proprietary, what that means is that this is a computer that was specially designed by the company you bought it from, and it's not compatible with any other computers. If you buy a PBX from Nortel, if you want to get an upgrade to it, you have to go back to Nortel to get the upgrade, a new hard drive or some more cards to plug on. And if you want to plug on telephones, you got to go to Nortel to get those telephones. So there are no standards here. This is all specifically designed and built by one company, and they control what it is. Since it's not standards based and you can't mix and match, that means they've got a bit of a captive market, and so they end up being more expensive. The idea with a soft switch is that we use general purpose computers and then we run a software application on them to do the functions, which is a PBX. And so we could go to Dell and buy some regular PCs or servers and then get a software application from some company like ComWorks or something like that and run it on the general purpose computers to do our telephone switching. Now, the advantages here is that since they're general purpose computers, the hardware is cheaper. And if you want to get more capacity, you could just add more PCs. So we have better scalability. The downside, well, who did the quality assurance on that software application, which is doing our telephone switching? Who did the QA on the soft switch? Telephone switches are designed for uptime. And just as an example, if you want to sell something to a telephone company that they're going to put inside their central office, the requirement for reliability for that is 1 hour downtime per 40 years. Now, you'd need an advanced degree in statistical analysis to figure out what the overall reliability of the central office is, but that's the stat for one box inside a central office. Now we turn and look at the hardware in a soft switch. Well, maybe that's a Dell PC. Well, those things are pretty reliable, but how often do they not work? I don't know. And then the software application, how long does that work for before it crashes? I don't know. So the question comes down to one of price versus reliability. And in a PBX, everything is duplicated. They have 2 of everything. They've got 2 processors, 2 hard drives. They've got 2 physical connections between every line card and the processor. It's called the A plane and the B plane. These things work, and they've had a long time to get all of the bugs worked out of them. The digital PBX was invented by Nortel in 1980, so we've had decades to get all the bugs worked out. Now comes along some company that you may or may not have heard of before with a software application running on Unix servers. How long is that going to work for before it stops working? Well, they might have a number, but how can they prove that that's the right number? So this is a pretty simple distinction between the two ideas. One is a box that's expensive, but you've got a good idea how long it's going to work for before it crashes. Another one is a standards-based open system with cheaper hardware and easier scalability, but there would be questions as to what the availability and reliability of the system would be. Once we have voice over IP working inside the building, and whether it's implemented as an add-on to an existing PBX using a gateway, whether it's implemented by adding some cards into the PBX and using that as the platform for doing voice over IP, or whether it's implemented using a soft switch technology, in other words, throwing away the PBX and using general purpose computer platforms with an application and the LAN in order to do the voice over IP. Regardless of all of that, once we have voice over IP working inside the building, then of course the next thing we're going to want to look at is doing voice over IP between the buildings. One way of doing that would be to use the internet to connect the buildings together. So we would have all nice carefully controlled stuff inside this building, all nice carefully controlled stuff inside this building, and then we're going to use a you pays your money, you takes your chances network to connect the two buildings together. Well, that would be cheap, but who knows what kind of end-to-end voice quality you're going to get. Another choice for connecting the buildings together would be to use a dedicated line, but that sounds kind of expensive and you can only go from A to B over a dedicated line. A more enticing possibility for connecting these voice over IP locations together is to use a commercial IP service, and these are often called IP VPN services. VPN stands for Virtual Private Network. The idea here is that some service provider is going to go purchase routers from some company like Cisco and put them in different cities and connect them together at their expense to provide an IP network and then provide access to that. Now, the virtual private network part of the story is that we front end this IP network with equipment that's generically called VPN hardware. And what the VPN hardware does is talks to its peer across the IP network and uses encryption techniques to establish what's called a tunnel across this IP network. And what this means is that if you put a scanner or a probe or something onto one of these IP networks from where the user can get access to it, this is on the user side of the VPN hardware, and then you scanned it, the only places that you would be able to see would be locations that you had paid to establish tunnels to. You wouldn't be able to see any other locations. But there's still lots of other users' traffic going over the physical network underlying it. It's the encryption and the two hardware boxes talking to each other that make it look like only your traffic is going over there, and you can only have your locations and nobody else can see them as well. So that's the virtual part of the virtual private network. Since this is a commercial IP network, a managed IP service, the access is very carefully controlled. That means that we can start talking about some quality guarantees. The problem is that those quality guarantees were designed for data communications. And data is not very sensitive to delays. Like if an email arrives half a second late, nobody's going to know. But when we start talking about doing voice, when we look at quality considerations in an upcoming discussion, what we're going to find out is that delay and variability in delay is the key thing that ends up affecting the perceived quality of the speech. And so while using an IP VPN network gets us secure communications and we can start talking about some service quality guarantees, those service quality guarantees probably are not at the voice level. They're probably good enough for doing data communications. Another problem with this is that yes, you can communicate between your corporate or organizational locations natively, so you make up